All right, hi everybody. My name is Colin Hill from Columbia and the Flatiron Institute. Today I'm going to talk about early dark energy and cosmological concordance. This is work done with this group of people mentioned and pictured down here. And you can find full details of our analyses in these two papers on the archive. All right, so the motivation of early dark energy, I think many people are familiar with. We're watching this. The idea is that by introducing this new component in the early universe, we can resolve the H0 tension by changing the sound horizon measured in the CMB. So this is an example of the effect of introducing this new component. So this is the posterior on H0 from fitting the LCDM model to this variety of cosmological data sets, including Planck, and also including SH0ES in blue, and then the same data sets fit with this EDE model in red. And as you can see, that it brings the posterior into better agreement with the constraint from SH0ES alone, although it's worth keeping in mind, as I mentioned, that SH0ES is included in these fits as well. All right, so how does this work physically? As I mentioned a second ago, the idea is that this new field decreases the physical size of the sound horizon that's imprinted in the CMB, so that's RS star down here, which is of course just the distance that a sound wave can propagate in the primordial plasma from the Big Bang until the time of recombination. Or in terms of redshift, it's here CS dz over h of z. So in LCDM, there's just three numbers that are needed to compute this sound horizon. The physical densities of baryons, cold dark matter, and photons. And of course, we know the photon density from Firas, and then the baryons and the cold dark matter are fitted from the detailed shapes of the peaks in the CMB. So then we actually measure the angular sound horizon in the power spectrum of the CMB. It's basically just the inverse of the peak spacing that you see in the power spectrum. So then we have a prediction for RS star from knowledge of omega B and omega CDM. We measured theta S stars, and the only thing left to be adjusted in the model in order to get the angular size of the sound horizon correct is H0, which of course enters through the angular diameter distance to last scattering. All right, so in the early dark energy model, the idea is that there's some additional parameters that enter, which are going to affect the sound horizon. So there's not just these three densities that are needed in order to compute RS star. All right, so let's talk about the physical implementation of this EDE field. Generically, it's been modeled as a scalar or pseudo-scalar field that we'll label as phi. So the idea is that we start with this field initially frozen on its potential due to Hubble friction. So if we look at the Klein-Gordon equation in a Friedmann-Robertson-Walker background, it's down here at the bottom. The idea is that H is much, much larger than the mass of the field initially. So this Hubble friction term dominates and the field just sits there. So it acts as dark energy with an equation of state W equals -1. So then as time goes on, eventually the Hubble parameter drops below the mass of the field and it will start to roll. And then eventually it will oscillate around the bottom of its potential. And the effective equation of state at that point will depend on the shape of the potential. So for example, for classic m squared phi squared, potentially you get this oscillatory solution that you can work out pretty easily. In terms of the numbers, if you want this field to have most of its influence just prior to recombination, which is what's necessary if you want to affect the computation of RS star, the sound horizon as much as possible, then you need this this rolling action to start just prior to the redshift of recombination. And if you put the numbers in, you find that means that the mass of the field has to be on the order of 10 to the -27 electron volts. So it's a very light field, which motivates thinking about these axion-like particles, which are protected by a shift symmetry to have this light mass. All right, so then the final model building constraint is that you want to have an equation of state W at late times which is greater than 0, so that the energy density contribution of this new field decays faster than matter. Otherwise, if it sticks around to late times, it will mess up lots of other stuff that we've measured in cosmology. So the canonical potentials that people have considered are these axion-like potentials. We have a 1 minus cosine of phi over f raised to some power n. If n equals 1, that's the usual axion. But as I mentioned, but the axion itself does not work because the effective equation of state at late times is just W equals 0. So that violates this model building constraint. So n equals 2 or n equals 3 are both reasonable options. N equals 3 is a bit easier to compute efficiently. N equals 2, the oscillations in the field are very fast, so it's a little bit harder to track, but either of the options would work. You could even consider a non-integer value of n, but in some sense that's very fine-tuned since you're adjusting an infinite number of terms in this expansion. Okay, so in terms of the new parameters that are introduced, generally this has been looked at in terms of the fractional contribution of EDE to the total cosmic energy budget, which is shown here as a function of redshift. This is the type of model shown here that could potentially resolve the Hubble tension. So the field contributes something like 10 or 12% of the total cosmic energy budget around matter radiation equality, and then it rapidly goes away as it rolls down its potential and oscillates around the minimum. So the new parameters introduced are this FEDE, which is the maximal fractional contribution to the cosmic energy budget, and the redshift ZC at which that occurs, which is of course closely related to the redshift at which the field starts to roll. So that's two new parameters. And then the final new parameter that is introduced is the initial field displacement in units of the decay constant, F. So there's three new parameters, FEDE, ZC, and theta I. And one thing to keep in mind is that there's a highly nonlinear relation between these parameters and the actual physical scalar field parameters F and M, which appear in the potential. So it, might be more reasonable to consider doing the data analysis in terms of the physical parameters. And I don't have time to get into it in this talk, but in the bonus slides or in our paper, you can find reanalyses done in terms of those physical parameters, which do actually change the results to some degree. Okay, so of course the excitement about this model is that it maintains a good fit to the CMB power spectrum, for example, as measured by Planck, while using a higher H0 value. So shown here is the lambda CDM, CMB-TT power spectrum in black, and the EDE calculation using this model shown here in dashed red. And the H0 values, as you can see, have a shift as one would need to solve the Hubble tension. And the key to achieve this close agreement is this decrease in RS that I mentioned earlier. I should also note that it's very important to include the perturbations in this EDE field correctly in order to get this calculation to work out right. And over here we see the residuals, which are under 1%, up to L of 3000. But importantly, it's worth keeping in mind that the other cosmological parameters, besides just H0, also shift when you analyze the Planck data using this EDE model. In particular, the amount of cold dark matter and the scalar spectral index both increase noticeably. So this might motivate one to think about large-scale structure data. So interestingly, nobody had actually made a plot of P of K, the matter power spectrum, in these models previously. So we set out to do that. We wrote this code called class EDE, which is a modified version of the Boltzmann code class. And it's all available on GitHub, so I encourage you to go check it out. There's notebooks that demonstrate how to do these calculations and reproduce many of the figures in the papers. All right, so here's what P of K looks like. So these are the same models that I just showed you the CMB power spectrum for a minute ago. So on the left, you have lambda CDM in black, and then this EDE model in dashed red. And now you can actually see by eye, even on this log scale, that there are some differences. If you make a plot of the ratio seen here on the right, then the differences pop out even more noticeably. So this is at different redshifts. And the main thing that's generating these differences are the changes in the cold dark matter density and scalar spectral index that I mentioned a second ago. So in particular, there's a large increase in the small scale, sort of quasi-linear to small scale power predicted in this EDE model. And that's not due to some dynamics of the EDE field, but rather just to these changes in the other cosmological parameters. So this is interesting, of course, because we have surveys that have actually measured P of K on these scales. So here I'm showing the matter power spectrum at redshift 0.525, which is the central redshift of the dark energy survey data. And this is the rough wave number range that DES has measured, denoted in blue. And so I'm showing two different variants of lambda CDM. One of them is basically a fit to Planck data. The other one is the best fit model from the DES analysis itself. And then the dash red down here is the EDE model, basically just fit to Planck data. And what you could see, Planck plus CMB. And what you can see is that if you look at the ratio between these models over here on the right, that there's this pretty large difference in the predicted power from this best fit EDE model to Planck plus CMB versus what the DES data itself would prefer. So this increase here on small scales is potentially of interest. All right, and this suggests, of course, that including DES data or other large-scale structure data in the fit could have some influence on the preference for this model. So it drives these this change in P of K, as I mentioned, are parameter shifts, and one could have inferred this by looking closely at some of the parameter contours in previous papers. This is from Tristan Smith et al. So the panels to look at in detail here are this one, which show the 1D posterior on the physical cold dark matter density, which goes up a lot when you move from LCDM to EDE. And the physics of this is pretty simple. It's just that you need to compensate for the suppression of the growth of perturbations by the EDE field, basically an early ISW effect, which is trying to suppress growth. So you have to crank up the amount of cold dark matter to compensate for that. Similarly, there's an increase in the scalar spectral index, NS, which is due to the fact that there's a slight scale dependence to the suppression, which you also have to compensate for. So if you turn that into a prediction for sigma 8, or this S8 parameter, which is a combination of sigma 8 and omega m, you find that the best fit value is 0.84, which is noticeably higher than what you get when you fit lambda CDM to these data sets. So in some sense, this is worsening the tension between CMB and large-scale structure data. All right, I don't want to go into this in too much detail, but there's also some interesting physical effects due to the EDE itself. So you can look at these plots in more detail in our paper, but basically as you change the amount of really dark energy, you change how much of this suppression effect happens. So all the modes that were within the horizon at this critical redshift ZC are going to have their growth suppressed. So that makes sense. Similarly, if you change this critical redshift, then you change the scale at which this suppression happens, because you change the scale of the modes that are within the horizon at that time. So lower ZC means that you push to larger scales or lower K. But the dominant effect that comes into play when you're analyzing the data is really this shift in the other standard cosmological parameters. All right, so now let me come to our the details of our data analysis. So we ran updated MCMT chains using the full suite of large-scale structure data sets available. We also updated to use Planck 2018 data for the first time in these EDE analyses. I won't go through this laundry list in detail, but there's BAO data, and then these new data sets that hadn't been considered previously, the DES 3x2 point likelihood, and constraints on S8 from the hypersphere prime camp survey and the kilodegree survey. And we implemented all this using our class EDE code and this cobaya sampler. Okay, so first thing I might want to look at is whether there's evidence for early dark energy in the primary CMB alone. So this is just looking at Planck 2018 data. So here's the triangle plot. And you can look at this in more detail if you want when you watch the video. But the basic upshot is that there's a broadening of error bars when you fit Planck with this EDE model, but there's no major shift in any of the parameters. And in particular, the H0 tension persists. So the gray band here is CMB, and you can see that whether you use lambda CDM or EDE, the tension is still there. So you can turn this into then a constraint on the amount of this early dark energy that's allowed by Planck data. This triangle plot shows FEDE, the critical redshift log 10 of ZC, and the initial field displacement theta I. So this top panel here tells you whether there's any evidence for this EDE, and you get an upper bound of about 9% of the energy density of the universe could have ever been stored in this field at 95% confidence. All right, so then skipping ahead a little bit, we can look at a global analysis that includes basically all cosmological data sets, everything that I mentioned a couple of slides ago, but not including CMB, since the idea kind of is to see if there's a model where the global fit to cosmological data actually yields an H0 that agrees with the direct local measurement. So the story is quite similar to what you get with Planck alone, except that the bounds tighten further. So again, there's a bit of a broadening of the error bars when you go from lambda CDM to this EDE model because you have 3 additional parameters, but there's no big shift in the central value, and in particular, the H0 tension still persists. If we look at it in terms of this FEDE ZC theta I parameter space, we get an upper bound on the amount of early dark energy of 0.06 at 95% confidence. So that's the blue curve shown here. And in terms of H0, the H0 value is in 3.3 sigma tension with the direct SH0ES measurement. So even in this broadened EDE parameter space, the tension persists. Conversely, then, if you included SH0ES data, despite the existence of this tension, which might be a little bit fishy to include it, given that tension, if you do include it, the results are shown in red here. So you get sort of a weak, but less than 2 sigma hint of the component being present. But you know, the weight of all this additional large-scale structure data still makes it very difficult for H0 to move up enough to reconcile the tension. So, you know, this is why we stated that this EDE model doesn't really appear to be concordant, because one is always trading off, trying to weaken this H0 tension with a worsening of the S8 or sigma 8 tension. And if you look at the directions of the degeneracy directions in the 2-dimensional posteriors down here, you can quickly read off that story. All right, so summarizing all the different analyses that we did in the paper, the basic upshot was that only SH0ES is driving any preference for the existence of this EDE component. The cyan curve at the bottom here is the one that is the global analysis of all data sets without SH0ES. And if you look at this in the H0 1D posterior here, you can see that indeed, you know, this does not move enough to reconcile the tension. All right, so in the last few minutes that I have here, I want to talk about an extended analysis that we did following up on that first analysis, where we introduced a new likelihood for the BOSS redshift space galaxy power spectrum based on the effective field theory of large-scale structure, and used that to constrain the EDE model. So a brief review of this EFT approach. The idea is to do a first principles calculation of the redshift space galaxy power spectrum, similar to the way that we do first principles calculations of the CMB power spectra with Boltzmann codes. So our previous analysis that I just showed you, we had folded in a likelihood from BOSS for the redshift space distortions, which implicitly assumed standard lambda CDM early universe physics, and others have done the same, which of course is a bit of a risky thing to do when you're analyzing a model that is different than lambda CDM around the time of recombination. In addition, as had been shown in previous papers from Ivanov and others, the standard BOSS RSD likelihood does not use the full shape information that's encoded in the galaxy power spectrum, so one can get much tighter cosmological constraints by using this EFT approach instead. And the punchline of our analysis, as I'll go through in just a second, is that this one loop effective field theory based full shape likelihood is actually much more powerful for constraining EDE than the standard BOSS likelihood, which just contains the constraints on F sigma 8 and then distances from BAO. And as I'll show you, this further tightens the bounds on EDE. So first, as a quick warm-up, let me show you the fractional difference between a fiducial EDE model, one that resolves the Hubble tension, and the lambda CDM fit, for example, to Planck or to previous BOSS analyses. So this is just for one chunk of the BOSS state of this North Galactic cap in this low redshift slice. So on the left is the fractional difference in the monopole and quadrupole of the galaxy power spectrum. And on the right is the fractional difference in units of sigmas. So you can actually read off whether we have sensitivity given our error bars to these differences. And I should note that there's a bunch of nuisance parameters in this EFT approach. So what we did was we separately refit those in each of these two approaches so that any difference here is due to actually to differences in the cosmological model. And the biggest difference that you see in terms of what we're sensitive to given our error bars is in the monopole, and you see this wiggling offset, which is due to changes in the shape and position of the BAO wiggles. And then there's kind of a broadband difference in the quadrupole, but given the error bars, we're less sensitive to that. All right, so just in the last part of the talk, let me look at the constraints here quickly. So this is constraints from Planck plus this EFT likelihood for BOSS plus S8 constraints from these other large-scale structure surveys. So the previous Planck alone constraints are shown in green. Those ones I showed you a bit earlier. And then after you combine with BOSS and these S8 constraints, you get the blue. And then for comparison, the LCDM results are in red. So what you can see looking at H0 is that this EDE model really doesn't shift much compared to what you get with LCDM, comparing the blue and the red. And the data is so constraining that in fact, even the error bar doesn't broaden by that much. So formally, there's still 3.6 sigma tension with the H0 constraint from CMB alone. And the upper bound on FEDE is very tight at about 0.05 at 95% confidence, which is pretty significantly below the amount of EDE that's needed to resolve the Hubble tension, which is typically on the order of 0.1. And then one thing that I think is really cool is that we could compare this to what you would get if you use the standard likelihood from BOSS. So that's basically comparing the red here is using we're using this EFT likelihood, and the blue is the standard BOSS likelihood. And if you just look at the constraints on FEDE alone, you can see that the red is significantly tighter than what you get with the blue. And the basic driver here is what's already known, which is that the EFT likelihood gives you much more constraining power in omega CDM. And in this broadened EDE parameter space, that additional constraining power is really important for breaking degeneracies. All right, so let me just wrap up now. We saw no evidence for the existence of this EDE component in fits to Planck CMB only data or CMB plus large scale structure. We found strong upper limits on the amount of this early dark energy. Importantly, the CMB constraint, when treated as a separate measurement, is still in pretty strong tension, even in the context of this model. And the basic problem is pretty straightforward. If you want to increase H0, you have to increase the amount of this early dark energy, and then that leads to the increase in the amount of cold dark matter, sigma 8 and S8, due to the need to compensate this early ISW effect, and then that worsens the fit to large scale structure data. So the sum total of this trade-off is that the EDE model really doesn't seem to have the ability to restore concordance. I didn't have time to talk about this, but if you use physical priors and scalar field parameters, that further weakens the evidence for early dark energy, and you can see this in the bonus slides if you're interested. So my takeaways from this is that in terms of the theory, we should go back to the drawing board, think a bit harder if we want to solve the H0 tension. And then taking a broader perspective on the data analysis side, given new results that have come out from the strong lensing time delay community, TD Cosmo, as well as the measurements from Wendy Friedman's group using the tip of the red giant branch, perhaps the case for the H0 tension itself has weakened a bit. So I'll stop there. Thanks.